Okay, so next we're moving on to another way that we can express our equations, if you like, for our graphs. And it's called, as it says here, parametric equations. So this kind of paragraph here is when a Cartesian coordinate of a curve is represented as functions of another variable, often that variable's t for time, they are called parametric equations. All right, so this other variable links our x and our y values together. So for example, here we've got x equals cos t, y equals sin t. So in this case here, t is our parameter, and so t is what then links our x and our y together. Because when t is, say, pi on 4, you get a particular x value, and then you get a y value that is connected to that. All right, and the connection is the t this time. Rather than our Cartesian equations, we just have x and y in them. All right, so they're parametric equations. All right, so for example, so lines, we can have lines that find the Cartesian equation for the curve defined by the parametric equations. Says curve, use the broader term curve. Curve is a straight line, is a curve without any curviness, so just a line. Okay, so we've got parametric equations here because we've got this parameter t. So to find our Cartesian, basically we've got to eliminate the t. And so to do that, one of the most straightforward ways of doing that is say, okay, for this one here, where x is t plus 3, if we take 3 from both sides, we get that x minus 3 is equal to t. And so then what we can do is we can then take that and we can substitute it in here for this t. So when we do that, you get y equals 3 times x minus 3, 3 times x minus 3, take 4, and then we expand that, 3x minus 9 minus 4, and so y is equal to 3x minus 13, I believe. All right, so the Cartesian equation for this curve, straight line as it is, from these two parametric equations is y equals 3x take 13. All right, so that's if we've got parametric equations and we want to find the Cartesian. What about if we've got something else? So it says find the parametric equations for the line joining the points. So one way of doing it is to first of all find out what the Cartesian equation of that line would be. And so to find the Cartesian equation, we use the equals mx minus x1, use the point gradient form, and of course the gradient is y2 minus y1 on x2 minus x1. So if we keep going here, y2 minus 6 minus 0 over 5 minus 2, negative 6 on 3, which is negative 2. So put points in here. So y minus, I'm going to use a as 0.1. So the y value is 0 equals negative 2x minus 2. So y is minus 2x plus 4, I believe. All right, so that's our Cartesian equation. So now we've got to turn this into parametric equations. And so to turn this into parametric equations, we have to write x and y in terms of parameters. So a way of doing this, And it's not the only way of doing it, but one way of doing it is say, okay, well, I've got x in here. And so let's let x equal, oops, not let equal, let x equal to something with the parameter. Now, the easiest thing is just t, so let x equal t. All right, that really could be anything, but we don't want to try and complicate things if we don't need to. So just make it x equals 2. And of course, if x equals t, well, we just got to substitute the x, the parametric bit, the x in here. And so because it's simply just a straight replacement of x equals t, so y is equal to negative 2t plus 4. So there's two parametric equations that represent this. Now, as I said, we could have something else here, and whatever the something else here, well, this for the y would reflect that difference. All right, so that's a simple way. Let's just make x equals t. All right, so that is straight lines. Parabolas is another thing here. So parabolas find the Cartesian equation of the parabola defined by the parametric equations. Okay, again, when we're finding Cartesian equations, the same as we did before, we need to eliminate our parameter. And so a simple way of doing that is, let's take 3 from both sides here. And then we take that and we substitute that in here for t. And so y is equal to 2 times x minus 3, and the x minus 3 is squared. And then we've got to take 1. All right, we now need to, well, we don't need to, but we can if we want to, expand and collect like terms if we wanted to, or we could just leave it in this form here, which of course is the turning point form. All right, but you could, if you wanted to, expand, collect your like terms and have it in expanded form, polynomial form. Okay, so there's parabolas. Circles, so here we go with the circle. So what do we know? Here's a circle, nice circle here. Radius r, center at the origin. And so here's a point on that circle. And we know that the equation of this circle here is x squared plus y squared equals r squared, it should say, not r, r squared. I'm going to make that, fix that up in my notes. Is equal to r squared. And so what we also know from trigonometry is if we call this angle t, then the x value, the x part, using trigonometry is r cos t, this bit here. And the y part, again using trigonometry because it's the opposite, it's r sin t. And so the parametric equations that we could use for a circle with its center at the origin, radius r, would be these two here. And our parameter, of course, is t, and our radius, our circle, is r. All right, as it says there, the parametric equations for the circle of radius r, center at the origin. All right, it's all good. So what if we have some parameters? So you'll notice this parametric equation's got an extra bit on the end. So maybe this extra bit on the end, it's not going to be centered at the origin, but we'll get to that. Here we've got a 2 in front of both of those, so that's probably indicates that's going to have something to do with our radius. But we need to eliminate the t's. Now in this case we've got circular function cos t sin t. Now, if you remember back to one of our previous topics, we've got the Pythagorean identity, and the Pythagorean identity is that sine squared plus cos squared is equal to 1. So that's what we're going to work with here with this. So what we're going to have to do is we're going to have to rearrange each of those to get the sine or the cos by itself. So here for this, for x, 2 cos t minus 1, add 1 to both sides. Divide by 2 then, so we've got x plus 1 over 2 equals cos t. And for the y, 2 sine t plus, not equals, plus 1. Take 1 from both sides. Divide by 2. All right, and because we are using the Pythagorean, I'm going to, and we need sine squared and cos squared, I'm going to square those. So squaring the top, x plus 1 squared, squaring the bottom 4, cos squared, squaring the top, y minus 1 all squared, squaring the bottom 4, and that's sine squared. So what do we know here then? We know that sine squared t plus cos squared t is equal to y minus 1 on 4 squared plus x plus 1 squared on 4. And of course that is equal to, because it's the Pythagorean, it's equal to 1. So then if I take that result and times each of the terms by 4, it's because 4 on the bottom here, then what we get is we get that y minus 1 squared plus x plus 1 squared is equal to 4. And so there's our equation of our circle. So it's got a centre of -1, 1 and a radius of 2, this particular one. Now, of course, we can go the opposite way as well. So find parametric equations of the circle. So the opposite way, let's just shoot back here for a bit. So if we're starting with this, then we need to work back up this way here. So we need to make that side equal to 1 to begin with. Then we've got our 2 bits, which would be our cos and our cos squared and our sine squared. So that we can then go to the Pythagorean. So if we're looking at that, here we can say then that, okay, so if we divide everything by 9, x minus 2 all squared on 9 plus y plus 3 all squared on 9 is equal to 1. And so then we know that for the Pythagorean, x is to do with cos, so it's cos squared t plus sine squared t equals 1 is our Pythagorean, and so these things must be the same if that is the case. All right, so if that is the case, then that means that cos squared is x minus 2 squared on 9, and sine squared is y plus 3 all squared on 9. To get rid of the squareds here, we square root everything, both sides, so cos t is x minus 2 all over 3 times by 3, add 2, and so x equals 3 cos t plus 2. So there's the parametric for x, and for y, if we do the same kind of process, square both sides. So this time we've got sine t is y plus 3 on 3. Square root both sides, I should say, not square, it's already squared. Then times by 3. And then take 3. And so y is 3 sine t take 3. And so there is our parametric equation for that one. Okay, so next, ellipses. So here's a nice ellipse. There, this one's got the centre there. Semi-major and semi-minor axes, A and B. That's what these are called, semi-major, semi-minor, semi-mean and halfway. So from the centre to there, and centre to there, semi-major is A, semi-minor is B. All right, and so there's our Cartesian equation for the ellipse. So if we now link this to our Pythagorean identity, then remembering that the Pythagorean identity is cos squared t plus sine squared t is equal to 1, and we compare these, and then we'd say that cos squared t is the x squared on a squared, and the sine squared t is the y squared on b squared. All right, so if we now square root everything, so then we've got cos t is x on a, times both sides by a, you get x equals a cos t. Square root sine t is y on b, times by b, and you get y equals b sine t. All right, which looks very similar to the circle one, except this time the number here and here, they're not the same number for a start, and they're not the radius, they're the semi-major, semi-minor axes. But there are similarities to it. All right. Let's have a look at an example. So in this particular one here, find the Cartesian equation for the ellipse defined by. All right, so again, we're using that Pythagorean identity. All right, so we're wanting cos squared t plus sine squared t equals 1, which is our Pythagorean, so we need to rearrange this. So if I take 2 from both sides, I'll get x minus 2 equals 2 cos t. Divide by 2, x minus 2 on 2 equals cos t. Square both sides, x minus 2 squared on 4 equals cos squared. For the y, add 4 to both sides. 3 sine t. Divide by 3. Square both sides. And then we've got that. And so now we can put these two things here into the Pythagorean identity. And so when we do that, we get that x minus 2 squared on 4 plus y plus 4 squared on 9 is equal to 1. So we're an ugly looking one, but it equals to 1. All right, so there we're going to our Cartesian equation. So the Cartesian equation of that particular ellipse, it's got its centre at 2, -4, semi-major axis 2, semi-minor axis 3. Now, calling it semi-major and semi-minor are kind of a little bit arbitrary, but with the X it's sideways and with the Y it's vertical, of course. Alright, so from the center you go sideways 2, from the center you go up and down 3. Alright, to get to where so our ellipse is this way this time. Alright, starting to waffle on a bit. Alright, so there's a few more things we can do with parametric equations, but I'll save some more for next time. Yeah, for the circles and the ellipses, we're making use of the Pythagorean identity that we've done before. If you've got any questions, make sure you get some help with those questions, and as always, have fun.